Alright, last part of today is unions. So, we talked about intersections and how there is sometimes a portion of two inequalities that will share solutions. Unions are or statements, so the intersections were and statements. Now we're talking about or statements. So, for instance, this right here, x is less than 0 or x is greater than 10. And if we look at that, we got the diagram to the right here. These are all numbers that are less than 0, and these are all numbers that are greater than 10. There will be no overlap here, and that's why we have to say x is less than 0 or x is greater than 10. So when we look at the graphs of these, x is less than 0 is the first graph. So not including 0, but anything less than that. Not including 10, but everything greater than that for the second graph. And if we combine those two graphs, we get a statement of x is less than 0 or x is greater than 10. So we would have to look at those two separately. There's no overlap, but when we look at them together, that's why there has to be an or statement, and it's also known as a union. So the nice thing about or statements is when you solve these, you basically just have two separate simple inequalities to solve. Kind of like the intersection ones, except for the intersection ones, sometimes it's a little more difficult to see what's going on with those, or pulling them apart anyway. So anyway, to solve this, we've got two different equations here, and we're going to solve for a in the left one. So what I would do is add 4 to both sides, and we've got a is greater than 5. Alright, so we're going to keep that there. We've got an or statement going on, and then we also have this equation on the right. I'm going to add 4 to both sides, and we have a is less than 1. So our overall statement would look like that. A is greater than 5 or a is less than 1. And let's check and see what that graph looks like. So maybe we go 0, 1, 2, 3, 4, 5. And we're not including 5, but a is greater than 5. It would look like that. A is less than 1, not including 1. And there we go. Just like that. So that's the graph, and then our official solution would be right there. Alright, moving down to the second example, and that's all I'll have here. Alright, another or statement. We will divide by 2 on both sides. Solve for x, so x is less than or equal to 3, or, again, for this one then, we'll divide by 3. X is greater than 4. Let's see what this looks like on a graph. So let's go 2, 3, 4, 5. Okay. X is less than or equal to 3, including 3, and going that way. And x is greater than or equal to, or greater than 4, not equal to, looking like that. And there we go. So any number that would suffice for either of those equations would be a solution. So it's not going to work for one, but it would work for the other. For instance, if I chose the number 6, if I put 6 in for x, and if I did it for both of them, so let's say I put 6 in here, I would get 2 times 6, which is 12, less than or equal to 6. Not true. So in order for this to be a solution, it's got to work for the other one. So if I put 6 in here, I get 3 times 6, which is 18, and now I have 18 is greater than 12. So a solution will be something that works for at least one of those equations. If it's a number that doesn't work for either equation, it's not a solution. So the things that would not be a solution would be the number 4 or anything larger than 3. And we'll talk more about this tomorrow. The same rules still apply. If you multiply or divide by a negative, signs will flip. And there is one other possible graph that we'll look at tomorrow as well, but these are the main ones. And that's it.